Welcome to video 1.1, all about vectors. We're going to be talking a lot about vectors this year, so I thought it would behoove us to start with the basic question of what the heck is a vector. And at its most simple, a vector describes some kind of change. It could be a movement, it could be an action of some kind, but it represents some kind of change. And mathematically, we often say that a vector has two things. It has a magnitude, or some kind of definite size or length, and a direction. It goes in some direction and not in another direction. There's a bunch of different vector quantities we're going to deal with this year. We're going to very quickly get to velocity and acceleration. And it makes sense that these things would have a directionality to them, because I can be going, for instance, 5 meters per second in a particular direction, and it matters a whole lot which direction I'm going. Some other ones we'll see soon are, force. Later in the year we'll get to like electric and magnetic fields. Those are all vectors. Some things, though, only have a quantity, only have a magnitude, and don't have a direction, and we call these scalars. And these are just numbers. Some great examples of scalars are time. Something doesn't take 2 seconds to the left. It only takes 2 seconds. Mass. I don't have a mass of 80 kilograms forward. That's just my mass. Energy is another one we'll see. Electric charge, all these good things. These are all great examples of scalars, and we'll get a little bit more definition on what a scalar is. Mathematically, though, I'm going to draw us a little vector. Here's our vector. And I'll give it a name. I'm going to call this the vector v. And how do I know it's a vector? Well, I'm going to draw a little arrow on top of it, above it, and that is a vector. Now, it so happens that this vector goes about this far. It's got a magnitude. There's its magnitude. Its magnitude is its length. If I drew the vector longer, it would have a bigger magnitude. If it was shorter, it would have a different, smaller magnitude. It also points, up and to the right. But we can be a little bit more specific about this, and you can get a little bit more specific about this with a coordinate system. So we'll draw in some axes. Now, it happens that the vector that I've drawn, or at least that I wanted to draw, has an extent of 1, 2, 3 in the x direction and 1, 2 in the y direction. So this vector actually takes me 3 this way and 2 this way. And as a result, this vector v that points up and to the right, we actually we can write it as the vector 3, 2. Now you might notice that I've drawn my parentheses kind of weird with these little triangle braces, and that's because those are not parentheses, those are triangle braces. Vectors get special notation because a vector is not a point. A vector is not the point 3, 2. The point 3, 2 is right there. Vectors represent a change. So this vector that starts over here and also goes 3 to the right and up 2, 1, 2, 3, 1, 2. This is also the vector 3, 2. This is also the vector 3, 2. These are all the vector 3, 2, because as long as they have the same magnitude and the same direction, they are the same vector. All the vector 3, 2 means is from wherever you start, go 3 to the right and 2 up. Now, like I said, it does have a magnitude and a direction. We can get a little bit more specific about this by using a little bit of trigonometry. Now, you might notice this looks an awful lot like a right triangle. And so I can apply good old Pythagorean theorem to find the magnitude of my vector v. Now, as it turns out, to write the magnitude, what we do is we use this good old absolute value symbol. The magnitude of the vector v is given to us just by Pythagorean theorem, 3 squared plus 2 squared, so that's going to be the good old square root of 13. We could also use some of our trigonometry knowledge using inverse tangent or arctangent. In this case, opposite over adjacent, 2 over 3, and whatever our calculator tells us, that's going to be the direction, that's going to be the angle there. It turns out we can do a couple other things with vectors. We can also decompose them. So just like here we found the magnitude and the angle given the two components, we can go the other way. So let's say I have a vector like this, and I happen to know its magnitude. Let's call this the vector u, and it's got a magnitude of, I don't know, 5. and I happen to know that it goes at some angle theta relative to the positive x-axis, well, I can say, well, you know, I know that I could break this down into some x component ux and some y component uy, and I could apply a little bit of trigonometric knowledge, and you've probably done something like this before to recover this side. Though this is ux is just going to be 5 cosine theta, and this would be 5 sine theta. Why is this one cosine? Well, it is adjacent to our angle. This one's opposite our angle, if you remember good old SOHCAHTOA for funsies. So we can always find the components of vectors, and that's going to turn out to be really important. The last thing I want to let you know that we are capable of doing is we can add two vectors together. We can actually add more than that, but we can add two vectors together. And we can do it in two different ways. One is the head-to-tail method. So to do this, literally, I'm going to take two vectors. Here's my vector A. And my vector B. And I'm going to add those two vectors together by drawing them head to tail, as the name of the method suggests. And then to find their summation, I start at the back and go to the front. So this is the vector A plus B, which makes a little bit of sense. If I run this way and then run that way, the net result is that I went from here to there. The other method we can use is called the parallelogram method. Parallelogram. And what we do there is, I'm going to try to draw the same vectors, is we draw them actually starting in the same place. So here's my vector A, and I'm going to try to draw the same vector B more or less. There's our two vectors. And then what we do is we actually say, you know what, these look an awful lot like the edges of a parallelogram. So I'm going to complete the shape and draw my vector A plus B. And if I've done everything right, this should be identical. Obviously, I'm not a flawless artist. We're going to be using both of those methods this year. You might ask, how do we actually add them mathematically? Let's say vector A is our good old 3, 2, and we'll call vector B, I don't know, 3, -1. You might ask how we add them. Well, it turns out all we do is we take the x components and we take the y components and we add them up. So our vector A plus B would be 3 plus 3, and then 2 minus 1. There, and you can kind of see that makes some sense. We go a lot in the x direction, not much in the y direction. So here, once again, we just have a nice little vector. Let's call this, let's take our good old vector 3, 2 here. We'll call this vector A this time for fun. There's a couple other things that we can do with vectors. We can actually stretch them or shrink them by multiplying or dividing them just by numbers. So as you might imagine, here's A. If I asked you to draw what half A is, you'd probably draw something that looked like that, except you'd actually draw it. You'd probably draw something that looked like that. That points in the same direction as A, but is only half as long. And you'd be right. And you might guess that half of A would in fact be 3 halves, 1, and you'd be right. You can just multiply everything by a half. If you wanted 2A, you could just take A and you could double its length, which I haven't really left myself enough room for, but you can imagine that that's 2A. I could even have negative A if I really thought hard about it and just turn this around. So by multiplying by numbers, and I could get 3A, 4A, 5A, whatever I wanted, negative 17A. All I'm doing here is I'm scaling my vector up and down. I'm stretching it. And you might guess, and you might be surprised to find that this scaling effect is in fact why we call these bare numbers scalars. 1/2 here is a scalar. It's just a number. One of the nice things you can do with a scalar is you can take any vector, let's take again our vector 3, 2, and we can shrink it down so that its magnitude is 1. What if I wanted the magnitude of A to be equal to 1. Well, what I could do is I could take the old magnitude of A, which I happen to remember from our previous couple minutes ago, is root 13. And I could just say, well, what if I declare some new vector, and I'm going to give it a special little hat, as my vector A divided by root 13. So I'm going to take this and I'm going to say, well, that makes my vector 3 over root 13, 2 over root 13, which is a weird little vector. And in fact, if I do all the math, I will find that the magnitude of that is in fact just equal to 1. And this is the first of many of what we'll see this year, which is called a unit vector. Unit meaning 1, that it's got a length of 1. Unit vectors are really, really super important in math and science. And in fact, I'd like to introduce you to a very special unit vector, or two very special unit vectors today. So here's a little, my good old XY axes. There's two very special unit vectors I'd like to introduce you to. The first one goes by the name of I hat, and I hat is the vector 1, 0. Hopefully it's clear that has length 1 and it just points in the x direction. The other one that I want to give to you is its cousin, j hat, which is the vector 0, 1. And together I hat and j hat are really, really, really important because they form a little orthogonal basis. And what we can do is we can actually make up any vector we want based off them. So our good old buddy 3, 2, I could write as 3, 2. You will also see it written, though, sometimes as I hat plus I hat plus I hat plus j hat plus j hat. You'll also see this written sometimes as 3i hat plus 2j hat. And in this case, anytime you see a vector that's got a little hat on it, you know it is a unit vector. It has length 1. And this can be really convenient for us when we're dealing with multiple vectors at the same time. We won't always take this approach in physics. We'll often take it in other math classes. But it still can be useful. So let's take an example that might be similar to one that comes up on your problem set. Let's say that I'm here. Here is our little class turtle, Shelly. And Shelly walks very slowly, 10 meters north, and then decides to meander a little bit and go 20 meters off this way. And we happen to measure and know that this is exactly a 45-degree angle. And the question that we want to ask is, where does she end up? How far away from her starting point does she end up? And in what direction? So we kind of want to know the magnitude of this vector and the angle. Well, we could break all this down into components, and that is something that we'll do. But one way I want to do this is let's just adopt our little I hat and j hat notation. So let's have I hat this way and j hat going straight up again. And let's try to write her movements in this new notation. So instead of writing just 10 meters in this direction here, what we can do is we can instead write this as this first movement here, and we'll call it d1. This little vector going up here, we can write this as 10 times j hat, 10 meters in that direction. Similarly, for the second little run up here, 20-meter run, you could do a little bit of trigonometry, and I think you could probably convince yourself, I'm just going to do this, but you can always check my work, that this is in fact 10 root 2 I hat plus 10 root 2 j hat. And it kind of makes some sense that the I hat and j hat components would be the same. It is at 45 degrees. What is the resultant vector then, this total displacement? Well, it's going to be, oops, getting ahead of myself here. It'll be 10 root 2 I hat plus 10 plus 10 root 2 j hat. Our I hat component doesn't change. The only movement in the x direction comes from our second vector here. And our movement in the y direction just gets added up, 10 plus 10 root 2. And from there, you could go ahead and just calculate its magnitude and its angle as per normal with trigonometry, because now you know that now you know all the components of this guy. And we'll do that one in class.